Well, thank you very much for giving me this opportunity to talk here today. So I'm going to talk about the first light instrument behind GNAO, the Gemini Infrared Multi-Object Spectrograph. It's a mouthful, and we spent a lot of time figuring out how to pronounce it, and it's GIRMOS, so it's easy to actually say it. It's a project that's largely being led by Canada with significant support from the National Research Council of Canada, and of course the Gemini Observatory. And this is a community-led instrument that started off as a visitor instrument and then has now evolved, heading towards something that would one day be a facility instrument at the observatory. And of course, on this image, you might recognize one of the images from the James Webb Space Telescope. The goal of GIRMOS is one of the main goals of GIRMOS is to follow up a lot of James Webb targets and do more in-depth science. And very quickly, the instrument is being built by a consortium of Canadian universities and national lab, and of course with support from the Gemini Observatory. It's a complex project with a lot of components, subsystems that all come together and have to work together. And so we're basically leveraging all of the expertise within the Canadian community, particularly the work that was done as a technical pathfinder for multi-object adaptive optics called the Raven project that was demonstrated on Subaru. Now, one of the things that has been happening over time is that GNAO and GIRMOS are becoming more and more integrated, and you can probably tell by our talks that we're talking to each other and trying to look at the whole thing as a single program in a holistic fashion, particularly the science, the concept of operations, systems engineering, and of course software, because all of this has to work together really well to reach, the performance at the focal plane at the end of within the instrument. And so we're very thankful that the Gemini Observatory has been providing a lot of support, and we've been able to work very closely with the GNAO team. Now, you nicely summarized what GIRMOS does, and in a real nutshell, it's basically a quad integral field spectrograph that sits behind the 2-arc-minute GNAO field. And it is able to image through that field at the same time. You get a little bit of occultation from the pickoffs if you do wish to do simultaneous imaging. And the diagram on the right shows you the GNAO field, and the imager field is the square inscribed within it. And of course, each IFU is doing additional corrections so that you get very high angular resolution observations within the small field of view. And of course, when we set out to do this project, while we started off with thinking about doing a galaxy survey and optimizing a high redshift galaxy survey and optimizing the performance of the instrument, we worked very hard to fill in all the gaps and find a broad range of science cases that range from the nearby universe to the most distant universe, and with a focus on what we can do that JWST can't do easily. And of course, GNAO has also developed on its own set of science cases, and there's considerable overlap between the two. And here is just a laundry list of science programs that we have fleshed out for the instrument in order to really understand what we want to build. And a lot of these programs that are shown over here are a combination of imaging and spectroscopy. So we've tried to really see holistically what are the capabilities that we would like to have. Now, when you design an instrument, you want to get a set of requirements. And if you have a laundry list of science programs, it's hard to converge on a set of requirements. So we looked for the most challenging science cases in order to what we call cardinal science cases in order to figure out what the specific requirements of the instrument should be. And there are basically three specific science cases. One of the big ones, which I alluded to earlier, is doing a high redshift galaxy survey out to redshift 3 in depth in order to complement the local integral field galaxy surveys that are being done and fill in the gap of galaxy evolution from high redshift to low redshift. Now, some of this work has already been done, and I'll show you in a second. The goal here is to really amass a large sample in order to be able to look at all of the different axes of galaxy properties and how they impact the evolution. And one of the specific things you would do with an integral field spectrograph is measure the kinematics of the galaxy using line emission and AGN activity, et cetera, which is shown by the plot on the left. And you can start piecing together the dynamics and to some extent the stellar population of these galaxies. Now, the state of the art right now is the SINF survey. I'm not sure exactly how to pronounce it correctly. And they've spent a long time using the Symphony instrument on VLT to do AO and get high angular resolution observations of redshift 2 galaxies. Now, our hope is to push that by a factor of 10. And the way that's done is from the multiplexing and minimizing the overhead of observations, and also pushing the sensitivity of the spectrograph. And that's how we've approached the problem. Now, of course, ERIS has just come online from the earlier talk. So they're going to be pursuing their own guaranteed time program. So we're evaluating exactly what the goals of GIRMOS will be in light of ERIS and James Webb now operational. But this is our nominal plan. The other reference science program that we want to target is something that's high angular resolution. The distant galaxy survey is moderate angular resolution. And this is to observe central regions of globular clusters and looking at the kinematics of the stars in these regions and trying to understand if there is any evidence for an intermediate mass black hole by looking at the kinematics of these stars. Now, a lot of this can be done with, say, MUSE in its narrow field AO mode, but there's a considerable number of globular clusters within the plane of the galaxy that are highly obscured that GIRMOS would be ideal in targeting. So Yulia mentioned this, one of the other pieces, one of the other reference programs, particularly for the imaging mode, is looking at AO-assisted imaging of transients. And the goal here is not only sensitivity and image quality, it's also speed of being able to set up the instrument and GNAO. So we're working very closely with the GNAO team to understand the overheads and be able to target transients that will be found in droves in the near future. Now, so in the end, when we put all of this together, we basically have two instrument modes. One which will allow us to pick 4 objects from the GNAO field of view and do multi-object adaptive optics, and another where we can put all of the pickoffs right in the center so that there's a roughly contiguous field at the very center of the GNAO field and be able to do use the laser tomographic AO and do high angular resolution spectral imaging. And of course, the imager sits behind the pickoff. So if you wanted to, you can do simultaneous imaging. And that was normally the plan, but there are some complexities associated with that. With IR instruments, you have to nod, and the imager and the spectrographs have different integration times. So that's something that we're currently working through to understand. So just a little bit about multi-object adaptive optics. You might be wondering what the heck is that. And that's shown by the graphic on the left there, where you have GNAO that has its own wavefront sensors and the single deformable mirror. It'll be basically correcting the low-level turbulence. And what GIRMOS will do is use the information measured by GNAO about the atmosphere and correct the remaining turbulence along that specific line of sight with our own deformable mirrors. So that ensures that each spectrograph will have an optimal correction. And we've done some simulations to show that there is fairly dramatic improvement in image quality doing it this way. I mean, that's the litmus test. You have to show that there's a significant gain. And we're actually working on putting a test bed on Sky right now, probably in the fall of this year. We'll be doing this type of adaptive optics on a 1 meter class telescope to validate our plan. So taking all of that in summary and figuring out what are the requirements, GIRMOS essentially has 3 spatial modes and 2 spectral modes. So the spatial modes range from being able to cover, super seeing limited imaging all the way down to diffraction limited imaging in H-band. And the spectral modes cover RF 3000 to 8000 for being able to do more precise kinematic measurements. And when you change the spatial mode, you actually reduce the field of view because you have a fixed number of spaxels that are available to you, so you get smaller fields of view. And just for reference, the James Webb NearSpec IFU is 3 by 3 arc seconds, and it has a similar spatial resolution as our coarses mode. So we can pack fair bit more information in a single IFU versus what NearSpec can do. And we also get higher spectral resolution. So this, just towards the end of my talk, I just wanted to show you a little bit about the instrument architecture, and this kind of shows the flow of light traveling into the instrument, starting from GNAO and the various subsystems such as the pickoff arms and the spectrographs and the AO system. And we have our own calibration system to both do metrology calibrations for the instrument as well as spectrophotometric calibration. One important aspect of how this instrument works is information needs to be transferred between the Gemini real-time computer and GIRMOS. And that's one of the reasons why we have to work very closely with each other. So the instrument design is fairly advanced. This is just how it looks right now. Like any other Gemini instrument, has this nice T-shaped structure. And we successfully completed our preliminary design review 2 months ago. And so we're in the final design. And of course, we're also going to do some risk mitigation, and we're going to start building the cryostat next year so that we can retire some of the risks that are associated with the spectrograph. This is just a diagram of the pickoff system. You can see what it looks like on the top right. And the AO system is integrated with that. The deformable mirrors sit inside of this, and then the corrected beam goes into the spectrographs. And the pickoff system has 4 pickoffs that can access the full 2 arc minute field that we have available. And finally, this is how the IR spectrograph itself looks like. So it has 4 spectrographs. You can't see the one towards you and behind you. It's sitting in this blue square tube. You can see the one on the top and the bottom. And at the very center is the imager that's being led out of the National Research Council of Canada. And so there are really 5 instruments on this, within this cryostat, that have to work together to make GIRMOS a success. And of course, one of the important things that we had to do for the spectrograph risk mitigation is actually build the image slicer that was part of our project plan. And we built a prototype that looks almost exactly like what would go on GIRMOS. It's shown by the little figure below, just before our preliminary design review, to show that we have the capability in-house to do that. With that, I wanted to conclude my talk. So GIRMOS is going to be a powerhouse for doing AO-fed integral field spectroscopy in the future, particularly targeting large extragalactic surveys. That's something that James Webb will have a lot of difficulty to do, but this would complement its capability quite well. And one of the things that it also does, and Julia mentioned earlier, is this is also a pathfinder, essentially a scientific pathfinder for a similar instrument for the 30-meter telescope that would go behind its adaptive optics system called Nefarious. So we're in critical design phase right now. Our expectation is we will deliver approximately almost a year before GNAO first light will happen, and that year would be spent integrating with the GNAO subsystems before first light. Thank you very much.
Thank you, Suresh. All right. Questions? Come on. All right. Please, Stefan.
It's made on a single point diamond turning machine. Obviously, it's not turning it, but it's cut off, carved out. That's right. So yeah, you guys probably use optical contacting to put that together. Yeah, we're just using an aluminum block and then we're carving out the slices. So we don't need that level of finish.
Yes, the micro roughness is not so bad in the infrared. Is that the?
That's right. Yeah.
Okay. Go ahead, please.
I have two very short questions. First, I was wondering if there were any limitations on the position of the IFUs within the field. And the second one, it was more about how it converses with you said the possibility of doing imaging simultaneously. So I was wondering how the filters and the ranges, how does that talk to each other with the IFU?
That's a good question. So the figure over there shows you like each pickoff has a certain arc that it can position itself. So it has approximately slightly under half of the field of view where it can position itself. Obviously, there's a collision avoidance that we will have to do also. So a given pickoff won't be able to access the entire field of view. We will have some software that figures out what's the optimal positioning. And at least for the galaxy surveys, we have way more sources than number of IFUs available. And for the imaging part, so the nominal plan is to use the imager for telemetry and track where the IFUs are over time and use it for acquisition for the long exposure observations. So there's been renewed discussions about maybe using the imager as a science instrument while those observations are going on because you're collecting photons. Now, the challenge there is the integration times are quite different. The IFUs will integrate for about 10 minutes, and then nod imager will probably be 1 or 2 minutes. And if you want to get good image quality on your images, you have to find probably some way to nod the imager while keeping the IFUs in the same place as they were before. And we're very concerned about the gymnastics of doing that and whether it's worth doing that or not, especially with James Webb being able to do such great deep imaging. So that's why I kind of mentioned that it's under discussion whether, and our PDR committee said, do you really want to do that? Because it sounds hard.
Zach, questions on Slack?
No.
No. Okay. Let's thank Suresh again for a fascinating talk.
Thank you.